Hello, I guess it's time to get started again. I'm Charlie Wallace, and I'm an engineer in the Dam Safety Division at MDE. In this presentation, we're going to look beyond the permit. As Jennifer and John have brought up earlier, we want to try to avoid tunnel vision and working in silos. So to do that, we're going to broaden our vision of dams and look at how to construct it. So how is a dam built? And where does a permit fall in dam construction? Now, this audience is composed of people with varied background and experience. And the next 50 minutes is intended to be an overview of construction and construction inspection. Some testing will be described, and it's more complex than what we're going to just touch on here. But it's hoped that those that don't have field experience will gain some background and insight into what we're discussing. Some of the photographs are not of small dam construction, but they illustrate the practices that are used in construction of dams. Now, construction operates in the business world of contracts, and understanding construction contracts, it's like a roadmap that helps you understand and have established lines of communication and understand the authority that is present in the field. Now, an inspector may represent the owner of the dam. It may represent the owner's engineer. The inspector may represent the contractor, or as typically the case for this audience, is going to be the regulating agency. And depending upon who they represent, the authority of the inspector will vary. Here we go. Okay. Now, the title of this presentation is Cavat Impetor, which is Latin for let the buyer beware. So during construction, since somebody's going to be owning this dam, you need to have inspection during the construction to make sure that everything is being built according to plan and specifications. Now, let's say I need to build a dam. I might be a private owner, or I might be a developer who, after the project's completed, I intend to transfer the ownership to a homeowners association or a local government. I might be a government agency. I could be building a road or some other structure, and the dam may be a side issue, but still I need to build a dam as a part of the project I'm undertaking. And I might be a business or commercial entity. Maybe I want to build a recreational lake or something along those lines. Now, to build my dam, I'm going to have to enter into contracts. And first, I'm going to want to enter into a contract with an engineer. I need somebody to design the dam and to prepare the construction and contract documents so that the dam can be built. They need to obtain permits, administer the bidding. And then once a contractor is on board, the engineer needs to manage and inspect the construction, keep construction records and prepare as-built of how the dam was actually constructed, and then certify that construction not only to the owner, but the engineer may need to certify it to the permitting agency. I also, as an owner of a dam, will need to actually enter into a contract with a contractor, and that person is the individual that'll perform the work, that'll build the dam, and they have to obtain materials and provide manpower and do the actual work. Now, as the owner, I have certain needs. I have a schedule. I might need this dam to be online at a certain date in order to do whatever it is I need the dam to do. I need to have control of cost. Construction costs can quickly go out of control if they're not monitored, and that's where inspection helps. Inspection helps with the control of quality. I want this dam, as an owner, I want this dam to last, and I don't want to have to be doing undue maintenance. I'm concerned about liability. If the dam fails, it could do damage downstream. So it's important that this dam is built correctly, and that'll limit my liability. And I'm also interested in managing risk. I'm undertaking construction. It's not guaranteed that this is going to work properly. There's possible conflicts that may arise or something else that could prevent me building this dam. Now, in a typical construction contract, there's items you usually see. And it may be that I'm not very interested in administering the contract, so I'll just bid it out as a lump sum, which means the contractor says, I'll do it for so many dollars, and that's it. Now, if it's possible that there may be variations in the amount of materials or other items that'll use, you could have line items, which helps you have a little more control of the cost. Contingency items, that's for unexpected events and like that could occur during the construction of a dam. You may start excavation and encounter a buried tank that delays the project, or you have to undercut and bring other items in order to make things suitable. And these would all be contingency items. It's good to address this in the contract rather than not having it in the contract, because that way you have better control of the cost. There needs to be procedure in the contract for change orders when changes are needed, and a method for reviewing shop drawings from the subcontractors to do their specialties. And then finally, if it's something that you can't reach an agreement with the contractor on, if there is a change in the contract, a device known as a force account is typically used, where you keep track of time and materials and pay the contractor for that. Now, the permit is something that is actually issued by the government authority to control the work that's going to go on, and it's not the government itself isn't entering into this contract, but a smart owner will bring up about permit compliance and include the permit as a part of their contract to help them have control of the contractor and make sure the contractor complies with the permit requirements. The contractor is going to have a project schedule. He needs to mobilize his materials, his equipment, his manpower. And then while this is going on, they need to submit sources of where they're going to have the different materials come from for review by the engineer, and also shop drawings need to be submitted and reviewed by the engineer. And then once construction actually starts, erosion and sediment controls are usually the first order of business. And if it's a large project area, there's likely going to be a sediment basin that needs to be constructed, and this is all done first thing. And once these controls are in place, then the contractor can go and clear and grub the site, begin the earthwork, and contiguous with that, they would be installing utilities and drainage systems, since these things are usually buried. And then once all that's underway, then whatever the structure or the project need is will be done. And then finally, the site needs to be stabilized. And then if there is a sediment basin, that needs to be converted to a permanent stormwater management facility. Now, in my opinion, inspection is the hardest job. Usually the inspector has the least formal training, yet they're expected to know the plans and specifications. And this will often reference proprietary specs or national specs, such as ASTM and the Association of State Highway Officials. There's a variety of different national references, and an inspector needs to be familiar with all these. The inspector needs to be aware of the permit conditions. He needs to understand the contractor's means and methods. He has to understand what the contractor is thinking, and that's hard to do, how he's going to utilize his equipment and how he's going to attack the construction. Typically, the inspector will have a good rapport with the contractor and discuss with them what they plan to do the next day or during that day. But then when that day comes, it could have rained overnight or some other unforeseen circumstance may arise. Now, the contractor needs to keep his people moving and not just standing around idly. So he'll probably have them work in a different area, and the inspector needs to be alert to this and pay attention to what's going on. And then if there is a problem, the inspector needs to speak up immediately, because if not, the work will just keep on going and it'll be covered over. It's important to recognize that as an inspector, you're not a supervisor. You're not directing the contractor what to do. You're only accepting or rejecting his work. And a common saying is out there is you cannot inspect work you supervise. And that's the idea of quality assurance and quality control, is that you're giving an independent evaluation of the work that is being performed. It's important not to slow the contractor down. Now, if the contractor is doing unacceptable work, you're not slowing the contractor down. He's just not performing properly. But again, it's important to not come up and needlessly slow the contractor down. There can be conflicts in contract documents, and in a good contract, the priority of how the documents are to be viewed should be listed. And when I refer to special revisions, that's usually a set of specifications specific to this job, and it's the basic contract of the job. The inspector needs to have access to the engineer in case there's something that cannot be resolved by looking to the plans and specs. Also, there may be hidden obstacles, again, that weren't anticipated when the plans were designed, and there needs to be the ability to provide for contingency items when the need arises. There can also be conflict between plan sheets. In science, we know that two objects cannot occupy the same place at the same time. And one of my favorite examples is I used to review state highway plans is drainage always goes down to a stream or waterway, and that's the roadway also has to cross this waterway. So that's where a bridge will typically occur. So the plans will just show the bridge without the person that's preparing the erosion and sediment control realizing that there's a massive foundation that goes along with this bridge on each abutment. So I've seen sediment traps placed right where the excavation has to go for this bridge abutment, and that's a conflict. Again, when plans are being designed, there is usually specialization in the disciplines, and the left hand may not know what the right hand is doing. Then we get to the idea of constructability. What's on the plans, can it be built? And this is where the contractor makes his money. He has his area of expertise. He knows how to do this job, and that's what he's really bidding on, his ability to do this work. Now, a lot of times dams are put in inconvenient locations. On subdivisions, the number of lots that can be built determines the economic viability of a project, and dams and drainage often is put to the areas that they can't put lots on, so they're usually awkward property parts of the parcel to begin with. Utility excavations can be a problem because even though they're just shown as a single line on the plan, they may be very deep and require extensive excavations in order to actually construct and do the utility work. Again, we talked about substructures and foundations. These may not be apparent on the plans, but they're necessary and they need to be considered. And the size of trench and other type of excavations needs to take into account the standard width of equipment, and it needs to be wide enough to allow this equipment to do its job. There needs to be consideration for access of the equipment. How is it going to get there? And another area that's easily overlooked is groundwater. When you're doing work, you need to work in the dry. You can't be standing in a puddle and doing your work. And my recommendation would be before the work begins to walk the site, get familiar with it, take photographs, and not only of the site itself, but also look off-site, because a lot of times disputes arise with the neighboring property owners over the construction work that's occurring. And this way you have some evidence of what everything looked like before the work began. Also, it's necessary to have a pre-construction meeting. That way everybody gets to know one another, the lines of communication are established, and what is expected for complying with the permit. And this is stakeout is the first order of business, so the contractor knows where he's going to build things. And this is a detail of a straw bale dike. It's not commonly used anymore, but on the plans, a symbol would be this dashed line. A straw bale dike, as you can see in the illustration here, it's a continuous line of straw bales meant to intercept water flow, but it's shown as a dashed line on the symbol on the plans. Now, getting with the theme of our total presentation here, what you see is what you get. Not everybody's familiar with reading plans, and they interpret things differently. In this case, it was interpreted literally, and you have a dashed line of straw bales rather than a continuous line of straw bales. So the inspector needs to be alerted as to what's going on and why, and understanding the level of experience that the contractor has, and work with them accordingly. Now, normally during earthwork, you have stakes that are set offset, such as you see here, so that the contractor can control not only the vertical, but the horizontal alignment of what the work is that they are doing. You can see here, this would be for a vertical alignment, and then the width and that of this looks like an emergency spillway that's being constructed here. Next, and this is a major part of the dam construction, would be earthwork. And this is an illustration of what a cut would look like. Say you're cutting for a cutoff trench. This is the original ground line. And then here's our excavation and construction subgrade, to where you're going to start filling. And it's possible sometimes you have some unsuitable material construction subgrade, so you have to undercut a little bit. This will be a contingency item, and backfill this before doing the remainder of the work. Now, when you're going to perform a fill, say this is 10 foot deep, you don't want to just pour 10 feet of soil in here and then compact the top surface of it. When borrowed soil is brought in to fill in an and that either a cut like this or to start doing a fill up here, the material is usually fluffed. It has air voids in it, and the particles have been separated one from another. So you need to control the compaction effort to do this, to do a fill. So you would normally put a 6 or 8 inch lith in across here and compact that till it's acceptable, and then keep bringing the fill up until you get to the grade that you need to be at. Now, again, once you get to excavation subgrade, you want to make sure that the surface there is stable, that it's not pumping. Now, proof rolling, you may not be able to get large equipment in there. If you have the ability to do it, it would be nice to have a large dump truck that's full, that's tire wheels on it, so that you're concentrating the force on certain areas to see if the soil stands up or if it pumps and moves. And if you can't do that, you could even just walk it and press your heels into the soil and see if it supports you or if it's giving way. Here's a photograph of the cutoff trench being installed. It's been excavated then, and they're starting to bring in clay backfill material. There's a sheep's foot roller. It has little feet on it that helps to knead the clay, and that's the type of effort that's needed with clay to get the best compaction. And then here's an individual running compaction test to see that the soil is indeed as dense as it needs to be. The soils that we encounter during construction are either sands, which are like granular and are large size particles, or on the other extreme, we have clay soils, which are very small particles and they're cohesive and they adhere to one another. And in between that, we have silts, which are medium-sized particles. And these aren't the best materials to use because a lot of times when they get wet, they usually get very muddy and are hard to work with. Now, we need to test for the compaction and make sure it's acceptable, that we're getting the amount of soil in there, the density that we want, and that air voids and the like are removed, so that over the time, the soil will not settle. We try to settle it while we're doing the construction. And the Proctor test was developed to simulate what the compactive effort is of the contractor to see what the density of the soil in place should be. And curves are prepared when you do this. And originally it was a standard Proctor. And then over time, everybody got better. They used larger equipment and the methods got better and they were getting higher density. So they came up with a modified Proctor. When you're doing compaction, the lift thickness affects the density, the moisture content of the soil, and the compaction effort, how many passes you make with the rollers, all influence how dense the soil will be. And in-place compaction testing now is done with, used to be done with sand cones, but now nuclear density gauges are widely available and used. Now here's an example of an individual running a Proctor test. There is a mold at the bottom that the soil is placed in lifts, and then there's a hammer inside of this cylinder that's lifted and dropped, and then it's released and it drops a given distance, and you do this a set number of times, and you do this in a set number of lifts. And after this is done, you weigh the soil, and then you take the soil out, you add moisture, and then you repeat the test. And as you're doing this, you'll get a series of points that appear on a graph. As the moisture increases, the density of the soil increases, and this will go up to a certain peak. And then as you add moisture, the density of soil will start to drop off. So if you make a smooth graph between the points, you can determine what the optimum moisture content would be to give you the maximum dry density. And this is what is commonly used in the field. The different materials have different optimum moisture contents and they achieve different densities. Clay soils tend to require more moisture to get their optimum density, but they don't get to be as heavy as if you go up to a sand. A sand can get to be quite dense and it doesn't require as much moisture to achieve that optimum density. And then man-processed materials such as crushed stone can get to even be more dense. I've seen crushed stone that is more dense than what you would normally find with concrete. Here's a dam being constructed. We have a large sheep's foot roller. There's an intermediate size sheep's foot roller, which was probably used during the cutoff trench construction. And then here is a jumping jack, which is can just be handled by one individual. This won't apply the same effort that something like a large roller will do, but in hard to reach areas, this is what's needed. And we have an individual running a compaction test in the background. Here is a smooth steel drum roller, and this usually vibrates. This is more suited for sandy materials. Sometimes it's necessary to do an excavation in an existing dam, and rather than do a straight trench, it's desired to cut back into the dam further and to key in the excavation so that when you replace the soils, you're able to bind it into the existing dam in a better way rather than having one smooth surface for failure. Sometimes you encounter rock, and in this case, they're using a hydraulic hammer to break the rock up, and then you have a backhoe here, and a lot of times they'll have teeth on it too to rip the rock up and remove it. And if this doesn't work, then blasting would be required, and that's beyond the scope of what we're talking about today. Sometimes excavations occur at the foot of a dam, and shoring and bracing is required. In this case, this is what sheet piling looks like. This is placed, the work can be performed, and then the piling can be removed. Here's a real life example in Maryland where, in this case, it's a reservoir, and there's an underground structure here. But during construction, when this was excavated out, this wall for the reservoir started to move. So additional bracing was required, and additional fill was placed between the forms and the existing dam so that movement was arrested and stopped. Another example of shoring and bracing, this is at the toe of the dam where end wall is being constructed, and this will be temporary as well and can be removed after everything is completed. We've talked about needing to work in the dry. Sometimes diversion channels are needed, and it can be a large drainage area, and so the diversion channel can be quite large to divert the flow around the site. This is the dam, and the off-site drainage area is diverted around the dam so that the work can continue, and then this reservoir would be lowered and dewatered. Again, this is another illustration of the off-site water comes here. It goes into a diversion pipe, and it's diverted around the dam, and it'll go to the outfall and go on. And here's the dam itself, and then the pond has been dewatered. Coffer dams are used when you got to work next to a large body of water and you need to temporarily hold the water back. In this case, it's a rock place coffer dam, and the water reservoir remains in place, and on this side everything is being dewatered so that work can be performed. Also, sheet piling can be used. In this case, it was going out into the middle of a water body, but these are the different types of materials and methods for constructing coffer dams. Unfortunately, especially with small ponds, you're more likely to see this type of diversion take place where a couple pieces of water drove into the ground, and then you have a piece of plywood in there to act as a diversion or a coffer dam. And just be wary that, if this is something temporary and it's not creating a hazard to anybody and it's going to be short-lived, they may be able to get away with this, but this certainly wouldn't hold up if you had a large storm come. Dams have spillways, and the principal spillway is usually constructed of concrete pipe, ASTM-C 361. The pipe should have a concrete cradle, and that cradle should be placed on natural ground. And we usually refer to the spillway as being inlet controlled, and a riser will typically control this. And gaining popularity now are weir walls, where you don't have a pipe, but instead you have a massive wall with weirs at different elevations to control the flow. An auxiliary or emergency spillway is typically found as well, and that should be in natural ground and not placed on fill. And it has a flat level section to control the rate of discharge. Typically, a spillway principal spillway would be constructed offline in the dry, and it would be built first. And then whatever the drainage way is that is coming to the dam would be directed to that spillway, and the remainder of the dam could be constructed, unless, of course, the whole offsite area is being diverted around the site to begin with. Here's a photograph of the spillway pipe being placed and a concrete cradle, and you can see that the cradle is being placed on natural ground, and the concrete comes up to a depth of the spring line of the pipe, which is halfway up the pipe. Here's another photograph of a spillway pipe with the concrete already set, and this would be the impervious core, and just downstream of the impervious core is where the filter diaphragm, which is composed of sand typically, would be constructed. It's important that if it's a spillway pipe, that it have a straight alignment, that there be no settling or displacement of the joints, and everything should look smooth and have a good appearance to it. Concrete is one of the key ingredients that is used in construction outside of soils. And concrete is composed of cement and water, and that forms a paste, and that binds fine and coarse aggregate, which would be like sand for the fine aggregate, and then typically stone or gravel for the coarse aggregate. And over time, it's been determined that if you entrain air into concrete, that adds tremendously to the durability of concrete. When concrete's exposed to freeze and thaw cycles, it tends to deteriorate rapidly, but air entrainment gives it just enough flexibility that it withstands this better. And admixtures can be added to concrete to change the properties of it. It could advance the set time, it could delay the set time, it could add the strength, it could add other different features, but these are the typical ingredients that you would find in concrete. And the primary ingredient would be the cement, what holds everything together. There are naturally occurring materials that are called pozzolans, which have cementatious properties to them, and the Romans and the like in the past used these materials. Also fly ash, which is a byproduct of industry today, that has certain cementatious properties, and it can be mixed in with Portland cement to keep the cost down a little bit, and it still will develop the strength that is required. Now for Portland cement, you have type 1 is what is commonly used. Then if you are encountering areas that you need more sulfate resistance, there's type 2 and type 5. Sometimes you need high early strength so that you can strip the forms and put the structure into use sooner. And in that case, they typically just grind the cement finer so that there's a greater surface area and it achieves its strength earlier. Also, there's cements for low heat of hydration. If you're doing a massive concrete pour, heat can become a problem, and this is one of the different ways that they can use to try to control that heat. Concrete is mixed, and typically it's mixed in a concrete plant, and it can either be wet mixed or dry mixed. And if it's wet mixed, the water is added to the concrete at the plant. And if it's dry batch, then the materials will be mixed and added to the concrete mixer without adding the water. And then when the truck arrives at the site, the water would be added there. It's important to have a timestamp as to when the water is added, because concrete will stop being plastic and start to set up usually in about 2.5 hours. So you want to have your concrete in place in the forms usually within an hour and a half, and it's important to watch time once the water is added. And you have to watch that when you mix concrete, it's desirable to add all your water within the first 10 to 15 minutes while mixing is occurring. And beyond that, you don't want to be tampering with the concrete and adding more water. Contractors will like to do that because they may be moving slow in their placement operations, and they need to have the truck sit there for a while, and to try to keep it workable, they'll add water, but this isn't a good practice. And again, there's admixtures that can be added to the concrete to adjust the setting time. There are standard concrete tests, the slump, which is a measure of workability. Air entrainment, again, if you have air that's added to the concrete, you want to make sure it's there and not have too much. You need to check the temperature of the concrete. And in some cases, you want to check the unit weight if you're worried, for instance, about anti-flotation, and that you have enough weight in the concrete that the structure is not going to float. You can check the unit weight to see if it's consistent with what was intended in the design. And typically cylinders are cast to determine the compressive strength, and they are broken 7 days and 28 days after they're cast, and 28-day compressive strength is what is normally specified, and that's the industry standard for accepting concrete. Here's a photograph of an individual performing a slump test. This is a slump cone, and it's placed on a flat surface in the other direction from what you see here. And the concrete is placed into this cone, and then that cone is carefully lifted off, and the depth that the concrete slumps over is measured, and that's a measure of workability. 4 inches of slumping is what is a common slump that would be specified. Some cases they want it to be tighter than that. In some cases they want it to be wetter where it slumps over further, but it's one of the specifications, and this is what the test looks like. Here's an example of somebody checking for air entrainment, and this is a pressure meter. The concrete's placed in this mold, and then the top is put on, and they're able to determine the air content from this machine. Now, concrete isn't always placed in ideal conditions. A lot of times it has to be placed in the winter or the summertime, and there's measures that can be used for that. If it's placed in the winter when it's cold, you don't want it to freeze. So blankets may be placed over the forms, or if it's a large pour, they may be able to find a way to add heat to it. In the summertime, ice can be added to the concrete and counted in the water that's being added to the concrete, and that helps to keep the temperature down. And you want to cure concrete. And as shown in this picture, here's some plastic that had been spread over the existing slab that we're looking at. You can use plastic. There's also curing compound that can be sprayed over it, which performs a thin plastic shield, but you don't want the water to evaporate too quickly so that the curing can take place properly. Also, you can't always back a concrete truck up to where you need to have the concrete placed. And so pumping trucks are often on site to where the concrete mixer can discharge into the pump, and then it's pumped hydraulically to where it needs to be placed. And this is an important part of placing concrete, is vibration of the concrete. It's a two-man operation. You can see here one individual is holding the power, and then that's applied to this vibrating rod, which is inserted into the concrete, and that helps to disperse it uniformly. It gets it into all the gaps, the nooks and crannies, and it helps to prevent honeycombing. We also want to avoid segregation. If you drop concrete a very large distance, the aggregate will separate out from the concrete and cement paste, and that's not desirable. So in this case here, there's an extension chute that was added to the concrete mixture to limit the amount of fall going before the concrete was discharged into these buckets. Once concrete is set up, cracking and spalling, honeycombs and cold joints, these are all things that are not desirable, but they occur. Here's an example of what spalling looks like, where the face of the concrete busts out, and then here's a crack. And then honeycomb would look like a bee's honeycomb, where you have voids in the concrete surface. And a cold joint would be where, if you're doing a large pour and you've already placed some concrete, and then either equipment's malfunctioned or you're waiting for the next truck and it hasn't shown up, and it gets to be a large period of time between trucks, the initially placed concrete will start to set before the next fresh concrete is placed next to it. And that can be unsightly, and it can make a unconformity in the concrete, which could be detrimental in the future. Concrete is good in compressive strength, but terrible in tensile strength. So reinforcing steel is added to give a concrete structure that tensile strength that's often needed. Here's a photograph showing the formwork for a riser. You have both an exterior forms, and then you have interior forms, and then the reinforcing steel is being placed. And this is good workmanship here. It's nice and neat and orderly. Everything's plumb, and at 90, the rods are at different angles, at 90-degree angles to each other. It looks very good, and this is good workmanship. This is what the inside of the forms will look like. There's adequate spacing between the rebar, which is a nickname for reinforcing steel, and the forms. These are ties which hold the forms together, and they'll remain in place once the forms are stripped. It's important to brace the forms too. When you add the concrete into the forms, it exerts a lot of pressure on the forms, and it's important to keep this in place. And spillways need to be watertight structures. Here's a riser that is being constructed and the base has been poured. We have the initial reinforcing steel sticking. It was embedded in the initial pour. It sticks out, and half of this water stop was also embedded in the concrete in the base. The walls will be formed on top of this, and then when that concrete is placed, this will provide a nice impervious barrier in the joint so that water can't leave it. And notice that this water stop also goes around the spillway pipe. Dams leak. So to control seepage, we have filter diaphragms and toe drains. This is what you commonly see in dams. And here's the outlet pipe for a filter diaphragm. It's adjacent to the outlet of the principal spillway. This is a filter diaphragm being constructed. You will note that the filter diaphragm itself, it continues on this side, and it will go underneath of the spillway pipe and continue on this side. The concrete cradle has not yet been poured, but they've excavated down to earth, and that's being ready to do the pour of the concrete cradle. Now we're getting close to the surface of the dam, and you can see that the filter diaphragm can be quite large. You'll have your spillway pipe, and then it extends quite a bit of distance on each side as has been designed. And this also needs to be compacted. You can see a compaction test is occurring here on the filter diaphragm material. And I can't tell you how many times somebody has said, wow, there's a natural spring in the dam. No, there isn't. There are no springs in dams. If you have water coming out of a dam, that's a sign of seepage. And not only can it just be, actual water flowing through the dam that you can see, but you may have soft spots that occur on the surface of the dam, or there may be an area where you have exceptionally good vegetative growth as compared to surrounding areas. You also need to look downstream of a dam, and that's why we insist on having a woody-free vegetation area downstream of the dam, is we're looking for boils, which would be where seepage is occurring. It's going underneath of the dam and then coming to the surface below it. And this is a way that a dam could fail. All the dams could fail from seepage. If it's okay, they leak. If it's just clear water that's coming out of the seepage, that's fine. But if it starts carrying the soils and the embankment material, then that's a real problem, and you need to get an engineer right away because the dam could fail. First filling is emphasized here. The first time you add water to a dam and put that load on the dam, if there's an imperfection or a problem, that's when it's most likely to make itself evident. So it's important to carefully monitor a dam when it's being filled for the first time, and to look for signs of seepage or any other imperfections. It's also a good look upstream into the pool or reservoir behind the dam. And if you see little whirlpools occurring there, that's also an indication that you may have water seeping underneath of the dam and daylighting downstream, and that's something that needs to be investigated. Now here's the construction of a dam. You typically have a stream flow going through a valley, and you want to construct a dam across this valley. The first thing you would do is build this new spillway, and then you would redirect the flow to this new spillway, and then you can continue on with the construction of the dam. And when we have certain nomenclature that we use with dam construction, if you're standing on the dam and looking downstream, this would be the right abutment, and this would be the left abutment. And it's a common feature that where the original stream flow was, is you'll see seepage. The geology of the stream bed itself tends to be slightly different than that of the adjoining areas. And this is a common feature that you see. It's nothing to be alarmed about, but you always, again, want to monitor it to make sure that it's just clear water that's coming through there and there's no sediment that's coming with it. We talked about auxiliary or emergency spillways. These are on native ground, and typically they're just grass covered. And this is the case here. It was envisioned that there were going to be flows with high velocities, so articulated concrete block is being placed on it, which will withstand the force of those flows. But you can see a variety of different surfaces on these spillways. And then finally, this is what landscaping should look like for a dam. It should be just clear, clean grass on a good stand with no woody vegetation. This way you can inspect it and clearly see if there's a problem. And then now we've been talking about dam construction, but sometimes we have to remove a dam. So I have a short video that I've included here for fun. This is an existing concrete dam. This first section here was just blasted. You can see the blasting mat in the foreground here, and the high water behind the dam is now drawing itself down to equalize with the river below it. I wasn't sure if that'd be This is more typically what you will see for a breached dam. It's an embankment dam, and there's grass on each side of where the breaches occurred. In this case, they were using straw bale dikes to try to control the flow during the breach and allow it to stabilize. And clearly this is not adequate. A better stabilized channel needs to be constructed. So this breach had to be redesigned. Also, a lot of times, even though something in dam safety, we usually specify a cast in place riser, but the contractor may still somehow get precast sections onto a site without our knowledge. And then once it's on site, we have to deal with what's there. And in this case, we required the joint between the two sections of precast riser to be epoxied. And there was just one strap that was going to be used. So we had the engineer look at it, and turned out they needed 2 straps on each face. So we also had them put 2 straps on, and we also had them put mastic around the entire joint too. And also with the precast riser, the opening wasn't custom made for this spillway pipe that was inserted. So it's brick and parged to try to make it watertight, but this isn't as durable as if it was cast in place properly. Slip lining. A lot of times there's existing corrugated metal pipe in the field on dams, and these tend to rust and deteriorate. And if you inspect the dam regularly and find that the corrugated metal pipe still has some integrity to it, you can slip line. In this case, it's HDPE pipe. It's slightly smaller diameter than the existing pipe, and this can be inserted in there, and then the space between this pipe and the existing pipe can be grouted, and you get a very strong structure that can extend the life of the spillway. Notice also that they're working in the dry here. In this case, it's timber cribbing that's used to give them the dry area. One section of this pipe has already been inserted into the corrugated metal pipe. The next piece of slip lining pipe is being attached to it, and usually there's a large piece of equipment like a backhoe with a bucket, which will push it in. We also encounter cases where a permeable material like gravel or stone is put underneath of a riser base, and that's not desirable and that's not allowed. And in these types of situations, they need to grout the voids between the gravel particles to make it almost act as if it's concrete and to make it less permeable. And grout is simply water and sand that's mixed together, and then it's injected under pressure. Sometimes an existing roadway serves as a dam embankment, and for one reason or another, a new spillway pipe needs to be placed in the dam. And since a lot of roads can't have open cuts because of the traffic that's on it, instead you tunnel underneath of the roadway, and the process is known as jack and boring. And this is a jack and boring machine here. There's also political considerations. Construction doesn't happen in a void usually. There's a surrounding community and neighborhood, and people are interested in what is going on. And in this case, this is something that had statewide notice, and we got the Department of the Environment Secretary Ben Grumbles being interviewed on a local network television station. So as an inspector, you need to be aware of what is occurring and how it is affecting the surrounding community and how it may be affecting the political jurisdiction in which you are working. Constructability is an issue. And this photograph was taken the year that we had 80 inches of rain. The sediment basin is at the low point of the project. Everything is draining to it, and it was a muddy mess to get down here to construct this and to bring the materials in. And as an inspector, you need to be aware that the process still goes on properly and you get the good quality that you're looking for in your dam when it's being constructed. Also, sometimes you have to get a large piece of equipment to efficiently get form work and other materials to where you're doing the construction. This is at the base. There's the dam here, and this is at the base of it, and they're getting ready to work on an end wall. And some final thoughts. You can't assume that people are going to read the permit. The contractor has been doing this business for years, and they're out to make money, and they believe they know what they're doing, and they assume that every permit reads the same, and that's not always the case. You can't also assume that the contractor is going to follow the plans. Where the contractor makes his money is in his knowledge and ability to do the work that's required, and they may have shortcuts or other features that they follow to get the work done where they can make a maximum amount of money, but a permit may require a certain sequence of construction, which provides protection for environmental features and the like. We are all creatures of habit. When I started out, I would tell a contractor do something differently than what he was doing. And he'd say, well, I've done it this way for years. And now you're telling me I'm wrong. And of course, as a young guy talking to somebody maybe a few decades older than myself, that was a bit of a challenge, but I would just have to diplomatically tell them, well, this is what's approved on the plans, and maybe this is a better way to do things. And usually they would cooperate. They had to cooperate, but it can be challenging for the inspector. And for engineers and for reviewers, if something is unique, if it's something that's important and critical, you need to call it out on the plans. There's a lot of verbiage on the plans. It's called boilerplate that is standard on from plan to plan, from job to job, and it almost goes into the background. But if there's something different and unique, you need to call it out. It's important to test and operate everything that's constructed. Many risers will have like a lake drain valve, or there's a gate. These types of things need to be operated and make sure that they're working properly. And when construction is virtually complete, it's referred to as substantial completion. And then the contractor will typically start demobilizing and taking their equipment and personnel and taking them to another project. But there may be items remaining. So a punch list is prepared where the inspector does a walkthrough with the contractor and engineer, and you determine what remains to be completed so that you can say that the project is done. And then finally, the final documentation, the as-built. How was the project actually built? What is here as opposed to what was planned? This all needs to be noted on the plans and any other documents that the contract may require. And with that, moderator, do we have time for any questions?
Yes.